Simon, do you remember? So it was an EA thing.
It's currently, it's just a speaker. So, this is the microphone.
Maybe it'll work with that one if it's close enough. Okay.
Well, it's currently unmuted.
Okay.
Maybe try it.
Okay, yeah, sure. Yeah. So I think behind all those applications, researchers and developers must have spent lots of time in terms of steering language models' behavior, because language models, especially those unaligned language models, often exhibit some undesired behaviors, such as hallucinations, untruthfulness, and toxicity. And there are lots of research around these undesired behaviors. And to fix them, and sometimes they even like incur real-world consequences, like the incidents happened with Air Canada. So because of all these undesired behaviors, alignment has become a very important techniques and research topics. There are lots of ways to align language models with human expectations, like the fine-tuning that we have been discussing, including instruction tuning and reinforcement learning from human feedbacks. And at the same time, there's another line of research that's trying to understand and study all these undesired behaviors by looking into how language models works, trying to get in some interpretability insights about, for example, how knowledge is stored within all these transformers and what's the semantics of those hidden states within these transformers. And it will be very cool if we can, by understanding how language models work on the hood, and develop some cool techniques or insights to guide alignment of language models. So for today's talk, I'll talk about how can we use interpretability insights to aid alignment of language models. And particularly, I will focus on the fine-tuning part and show you how can we use some interpretability insights around localizations to aid fine-tuning of language models in an efficient way. And specifically, I'm going to talk about our recent work, localized fine-tuning of language model representations. And this is a collaborative work I did while I was still studying my PhD at UT Austin. And I would like to especially thanks to my amazing mentee, Feng Congyin, for leading this work. So a little bit background on what we are trying to achieve and our goal here. So again, we are trying to steer language models. So for instance, if we ask some language model this kind of question containing some common misconception, like what happens if you smash a mirror? And some people, actually lots of people believe that breaking a mirror can lead to 7 years of bad luck. This is a kind of common misunderstanding that persists, that repeats a lot in the pre-training data. And even early versions of GPT-3 will make this kind of wild answers. And we want to adapt the language model in order so that it can answer, it can give you a truthful answer. And we want to do it in an effective and efficient way in terms of both data efficiency and compute efficiency. A little bit refresher on the transformers, as we are operating and steering large language model, which is built on transformers. So a large language model has a lot of transformer blocks, and typically each blocks will take as input a hidden state from a previous layer and go through some multi-head attention, where each attention head will give you one hidden state. And then we concatenate them together and go through another MLP layer to output the representations for the next layer. And here we have the activations of the MLP layer and the activations of the attention heads here. And we'll call them representations of language models used within transformers. Okay, so here are all the backgrounds we have set up, and feel free to interrupt at any point to ask questions about the approach. And now we're gonna give an overview of our approach, which is localized representation fine-tuning. So our approach has 2 steps. First, we'll select a set of attention heads. and we're going to select a sparse set of potentially impactful attention heads. It can be like 10% or even 3% or 2%. And it's only a very sparse subset of all the attention heads used in the transformers. And for the second step, we'll learn an offset vectors only for those selected attention heads. And the offset vectors, it's an offset for the representation space. And during inference, we add those offset vectors back to the representations. So here, there are two distinct features about our approach.
What's a vector? In which case is a vector?
I will give a little bit more details on like how we do the intervention. At this step, like the high level idea, just like we're learning some external vectors or parameters that we'll be using to operate on the representation space, and how we are going to intervene on the representation of the vectors. I'm gonna like cover that in next probably 3 or 4 slides. Yeah. So there are two kind of the most distinct features of our approach. First, we operating on localized modules. We only operate this kind of operations on a small set or on a sparse set of like attention heads. And second, we're intervening on representation space instead of the model weights. So we're not touching the KQB matrix within attention heads. We're only operating on the representations, specifically the activations output by the multi-head attention. I'm going to explain why we make such two choices. It's all coming from interpretability insights we have about language models' behaviors. So for the first point, localizations. There are lots of research on trying to localize knowledge and skills within transformers. And actually, language models' behaviors, including knowledge and skills, can actually be localized and edited. For a very common kind of instance. So for this like rapidly changing fact, the prime ministers of UK, if we ask a kind of outdated language model, who is the prime minister of UK, it might give you an outdated answer. And it's actually possible to trace this knowledge back to a single layer of the transformer, specifically a single MLP layer of the transformer. And then we can just edit the weights of that specific layer without touching the weights of other layers. Just by editing a localized part of the module, we can change the answer or injecting the new knowledge into transformers. And there are lots of research in terms of this operation, editing knowledge or injecting some skills. And the motivation here is if we are able to make the edits in a localized fashion, we're able to do the edits in a more lightweight. The localized edits are actually more lightweight, and we can potentially affect the other aspects of the language models less heavily. So for the second feature, we operate on the representation space instead of the weights. We have lots of research on the representation space as well, trying to decode what semantics the representations contain and what the representations can tell us. So representations are actually interpretable in some sense if we use some special techniques like probing to decode some certain behaviors out of the representations. Suppose we have a bunch of questions from the truthful QAs, and then some of the answers, and then ask language model to give the answers. Some of the answers are truthful, and some of the answers are untruthful. And we plot the representations on the representation space. We can actually find a kind of direction, and by projecting those representations, we can separate the model behaviors using these directions. Here we denote this as a truthful direction. So it is a cool thing because even though that the model is outputting untruthful answers in these cases, but we can get to know more about the behaviors by looking at the representations. The representations can actually tell you that some of the answers are more truthful and some of the answers are not so truthful. So in some sense, the models are already knowing that they are producing like good answers or bad answers without being like question.
So this truthful direction, is it relatively homogeneous across different domains and questions?
So for different concepts, like the direction is kind of different. So this is like feature for a specific behavior, which is about the truthfulness, like on the specific data sets. Yeah. Yeah, that's true. But like many of the behaviors has a like you do have a single kind of like scalar value kind of reward function that you can describe, right? For example, for example the truthfulness one. So it's actually kind of like expressive enough to cover a bunch of like behaviors we care about, like truthfulness, like toxicity.
What is that direction? So meaning there's a question and you say, and the choices are true and false, and you look at some
yeah.
What is that direction? Gradient or?
The direction. So each of the like the point here is a vector. Like essentially this direction it can serve as a kind of binary classifier on like the quality of the
truth.
Yeah, of the answers.
So, but it's like in the gradient kind of like.
It's kind of it's kind of like the weights for like of a classifier. Like if you train a classifier on the representations to classify things that's like.
I see. So it's a weighting of outputs in some nodes.
Yeah. You can view it as that. Yeah. So the point here is just like we can know a lot of things from the representations, and the cool part is we can actually intervene on the representations to change language models' behavior. So suppose like this direction, it tells you something about truthfulness. Like, and we can move a kind of red point along this direction so that the model will like give a more truthful answers. So this tells you something about like just the representations. It's kind of decomposable in some sense. And you can just like moving the representation along a certain axis to elicit the behaviors along that axis. And we are not the like first one to do this. There are lots of prior work showing lots of just recent interest in terms of just manipulating the representations to elicit some certain behaviors. And mostly they do it in a learning free way where they extract some kind of like directions using some heuristics and some kind of contrastive pairs in order to intervene on models' behaviors. And we're gonna show how we can just learn to localize and learn to extract the offset vectors in an end-to-end fashion. Again, going back to our approach, next I'll give some details on the two steps, especially on how we are like operating on the representation space. So in the first step, we are learning to localize attention heads. So basically, we'll try to scale the representation of a head with a factor. Given the outputs we obtain from the multi-head attentions, for each representations, we'll use a scaling factor to scale each individual neurons. And then everything goes like the same. We're just doing the normal concat and projection and passing through the MLP layers. And we'll learn this kind of scaling factors on the task. Suppose you're trying to suppose you are trying to adapt the models for truthfulness, or adapting the models for like to reducing bias, or just learning some patterns, we'll just fine tune the scaling vectors on the task you care. Question?
So each AIL a vector, not a scalar.
Yeah, a vector. So we are scaling each individual neurons.
You're not localizing to specific attention. You're localizing to elements of the algorithm.
Yeah, right. But like, so we have a scaling factor. Essentially, we have a scaling factor for each neuron. But when we are selecting, we only operate on the heads level. So that's what I'm gonna talk about next. Just basically, we'll select the top K attention heads using the largest normal scaling factors. So in the end, we're still selecting the heads.
So this seems a little unintuitive approach to do the full vector and then what do we say?
The attention heads, copies of attention heads, because there are many copies in the layer.
Yeah.
Which do you mean?
We select, so like for example, each layer has lots of heads, right? And like we're selecting, so maybe for layer 1 we select a set, for layer 2 we select a set, but overall.
But a head corresponds to a location.
Yeah.
Okay.
Yeah.
So I think maybe that was the question.
So once we got the attention heads, we'll then learn the offset vectors. So we'll do it in a similar fashion. But at this time, we'll add offset vectors instead of like scaling the attention heads. So basically, for each representations produced by attention head, we'll add another offset vectors, and then like everything goes the same. And it will also be learned end to end using the task you care about. So there's a little bit discrepancy in terms of like in the first step, we're using scaling. And for the second step, we are using the like offset vectors. And so we will come to this choice because of like first, intuitively, like if we are just scaling the attention, the representations, we're trying to like amplifying or suppressing some kind of like skills that the models already have, and trying to reuse those skills as much as possible. And for the second step, we're just like trying to add offsets following some intuition like we get in terms of like, for example, truthfulness like directions.
Truthfulness is not really a skill.
Yeah.
I mean, it's like basically, it's very close to prediction. But
yeah,
is there any other concrete skill for which you?
That's actually a good question. I will include a little bit discussion on what skills or what thing we can learn like with these things. Of course, like it's not gonna work for everything.
But the skill is a procedure.
Yeah. It's more or less like, so for this kind of things, because you're like manipulating the representations, it's more likely to learn something that the model already knows, that you can already probe from the representation, as opposed to like injecting using like doing arithmetics to the model. Yeah, so here are the tasks, 3 main tasks we're using. The first is the like we're gonna test on like models across 2 family and across skills. And for the task, we're gonna cover like the truthful QA, which is about like truthfulness, and the MCAT, which is actually a like data set developed here at LI on knowledge editing, and Clutter, which is multi-hop reasoning. And we choose these 3 data sets because it's like we can extract some kind of interpretable like conclusion from the representation, and they are like commonly used in the mechanistic interpretability research. Like we don't include like results on GSM. We try that, but that's not work like it doesn't work quite well on the like GSM if we have like lots of data, which we feel is not like suitable for this kind of like representation intervention techniques. And we try with like very low data set. And this data set typically just only contain a few hundred like data points. And because we're operating on representations, we feel it would be very like efficient to just like tune the model, intervene on the model a bit. So we don't need quite a lot of data. So first, the main result, we are comparing against the existing representation intervention baselines, which basically uses kind of heuristics for selecting heads or getting the offset vectors. For example, you can take the representations of all the like positive responses and all the negative responses and like get a difference between these kind of two representations and use that as the offset vectors. So it's kind of extracted in heuristic in some sense. And it actually works compared to, just like prompting language model zero shot. But we show that like by learning to locate and learning to extract the offsets, we get much better kind of like effectiveness in terms of intervention on all these data sets. So this learning-based localization of and offset vectors are more effective intervention. And it's true across like different models and different data sets. And the main part here we want to like discuss is the effectiveness of localization. Yeah. So we compare with like parameter efficient tuning methods because they touch on all the parameters. So because we do localization, so we actually touch on much fewer parameters compared to things like LoRa. But we actually achieve comparable performance. So we did achieve comparable performance even if we are modifying kind of like 200 times fewer parameters, especially compared to LoRa. So this indicates all this kind of like things we want to learn can actually be localized and can actually be attributed to a localized parts of the models. And we have this hypothesis because we touch on localized modules, we kind of affect models' other behaviors or general capabilities in a less like harmful way. So we directly train the model using our approach as well as some baselines on truthful QA and testing their performance on out-of-domain datasets. So we can see like using LoRa, we typically see a more kind of like a more obvious kind of performance degradation compared to the non-function part, which is the first column. But if we do localized edits, we can actually preserve the model's capabilities in general better. And we explicitly evaluate how important like it is to select the right heads. And we compare like the different head selection methods we have on the same kind of learning methods we on the same with the same offset learning steps as used in our approach. So we compare against like selecting random heads and like the probing, which is a typical, a commonly used mechanistic interpretability methods to localize heads. So selecting the right heads does matter. We can see using random heads, you usually don't get very good kind of performance. And with some kind of mechanistic interpretive insights, you select better heads. But it's important to do learning to localize the right set of heads in order to intervene on. And lastly, we have a like figure on like it's the heads you select very kind of like task specific, or does there exist a set of like magical heads that covers all the capabilities you want to like touch on? So here we're showing the distribution of selected heads over like across layers. So basically, like by just eyeballing these figures, you can see for different tasks, the distribution of layers are actually different. So each kind of like things you want to intervene on actually can be attributed to a like task-specific modules. And we do have more quantitative results in the paper. Okay, so the final takeaway here. We're operating on localized modules, and we're operating on the representations, which are the two key components of our approach, which is inspired from mechanistic interpretability research. And our approach can learn highly localized interventions, like 3% of the attention heads on the representation space in order to steer language models' behavior efficiently. And with one caveat, just like it's in general effective for like activating some skills that we already learned from the pre-training. And if you want to like inject, like for example, math reasoning skills using like 10,000 GSM data, that's not going to work very well compared to LoRa. Cool. Yeah.
Thank you so much for the time. In the interest of time, we're gonna have a few questions maybe in the other room. If you don't mind, maybe taking some questions. To give up